Let's go ahead and make the smallest possible Linux distro. For this, we're going to need a couple of components. The main one is going to be, of course, the kernel itself. But we also need a bootloader and some kind of user space. But we're going to start here with the kernel. We want to go ahead and build a very small kernel. As you can see over here, I have cloned the Linux repository. And I'm going to put information about all the setup in the description. First command I'm going to run here is make help. And it'll show me a bunch of options I can use to pass the make. And specifically, you can see it also includes configuration options. Like this is the default configuration for x86-64. I'm going to look specifically for an option that is called tinyconfig. You can see that this configures the tiniest possible kernel. So this is going to be the base of what I'm going to use. And to use this, I'm just going to run make and then tinyconfig. Now you can see the configuration is written. I'm just going to make a couple of changes. So I'm going to run here make and then menu config. First of all, I want to turn on the 64-bit kernel because this video is going to focus on 64-bit Intel. Afterwards, we're going to need to enable a couple of stuff. So I'm going to go here to general setup. And first of all, I want to go ahead and enable init ramfs support. This can be important to have support for the user space that we're going to build. So I'm going to check this. And we can go ahead and uncheck all these options. No need for the support for the special compression types. Now I'm gonna just scroll down a little bit more and make sure this is enabled on your setup. And I'm gonna press enter on this, configure standard kernel features. And over here, I'm gonna scroll to the option that says enable support for printk. And I'm gonna enable this so we can see actually messages that are coming from the kernel while it's booting. Now let's exit from here. Next, I'm going to scroll down here to drivers, device drivers. And here I'm going to scroll until character devices. And I'm going to enable TTY here. TTY stands for teletype. This is important so we get actual text on the screen. Now we can finally exit. And let's go inside of the executable file formats. And here, make sure to enable kernel support for ELF binaries. This is important because we want to run programs on the kernel. Now we can exit and save the changes. Now let's go ahead and run make -j4. This is going to split the make for 4 jobs. It'll make it faster because I have multiple cores on my computer. Okay, nice. Now we can go ahead and test this image to see that it works. I'm going to use QEMU for this to emulate a computer that is booting up. I'm going to use the -kernel flag because we're passing in a kernel image. And we can see the kernel is booting up nicely. And the kernel finishes by searching for the init process. It's trying all kinds of paths over here. And finally, it's giving up and panicking because it didn't find any working init. No working init found. Let's go ahead and fix this. But first of all, I want to show you how small this is, how small the kernel image is. Check this out, it's only 781K. Now let's go build the user space. I'm going to build a very minimal shell. It's just going to be a program runner. I'm going to start by a C file that I'm going to call shell.c. I want to start by writing something on the screen. I'm going to write the prompt of the shell. So I'm going to use the system call that is called write. First argument is the file descriptor, and that's going to be 1 for std out. We're going to write it to the console. Afterwards, the buffer that I want to write, and that's just going to be the prompt, so something like this. Finally, the count of bytes, and that's just 2 bytes. And afterwards, I'm going to read some input from the user. That's going to be the program to run. And for that, I'm going to use the read system call. By the way, I'm just going to remind that the code in this video is just going to be for fun, and it's not going to be for production purposes. I'm going to skip all kinds of important stuff like error checking, just to make everything here as concise as possible. Read has a very similar interface, also file descriptor, buffer, and size, just it's the opposite direction. This time we're going to use file descriptor number 0 for std in. We're going to get input from the user. Afterwards, the buffer, let's just call it command. And the size, let's say 255 bytes. So we're just going to put a fixed limit on the size of the command. I'm going to define the command over here. Now let's take a look at the return value of read. We're gonna assume success here, so on success, the number of bytes read is returned. So I'm gonna save this return value. Let's call it count. And now what I'm gonna do is I'm gonna replace the new line in the end with a null terminator. Let me explain. Let's say you put the command, for example, you wanna run ls, so you run /bin/ls, but the read system call is gonna return this and then a new line afterwards. So what we wanna do is we want to turn it into /bin/ls, and then a null terminator afterwards to terminate the string. Now the trick to do this is I'm gonna go to command, and I'm gonna go to count -1. And that is where the new line is gonna be. And I'm just gonna place a null terminator over there. Nice, so now the command is ready, so we can go ahead and execute it. And for this I'm gonna use the execve system call. First argument is gonna be the path name, and that's just gonna be command. Afterwards, we have a nullable argv. So I'm just going to pass here 0. Not the best practice, but again, this is just going to be a very simple example. And same for the np. And now we can just go ahead and test this out to see how it works. This is a very, very simple program runner that will run one program and then exit. Let's build this with GCC. And I'm going to use here, for example, /bin/ls. And nice, we can see it works nicely. But notice that it just exits after running this. We want it to continue receiving commands. I'm going to put all of this in a for loop. But this is still not enough, because running execv is going to replace the running process with the new process that is specified over here. So this will replace the shell entirely. We need to fix this. We're going to use fork for that. This will fork a new process, and then we can run execv in the child. So we can see fork creates a child process. We're going to do that before the execv. And it returns the type. I'm going to talk about the return value soon, but let's go ahead and save it right now. And now let's talk about the return value. On success, the PID of the child process is returned in the parent, and 0 is returned in the child. This is important because this is how we're going to know we're the child. So if fork result is 0, then we're going to execv. Else, again in this video we're not going to go ahead and handle the failures, so we're just going to assume that else we're in the parent. What do we want to do in the parent? In the parent we want to go ahead and wait for this to finish. Now this is the child over here. So for this we're going to use some kind of wait mechanism. Now one more thing I want to do here is I'm going to break from the loop in this line. Remember, this is the code that is running in the child. Reason for that is that if the command is good and execv succeeds, it's going to successfully replace this process with something else, as specified in the command. But if this fails, it's just going to continue executing the code afterwards. And I want it to break from the loop if it gets here, so the child won't become also a shell. Now let's talk about this wait over here. So we can see how we have quite a couple of options that we can use for wait, but I'm going to say something about this. Even though this is in the system calls manual, category 2, these are not actual system calls in the kernel. The only one here that is actually in the kernel is wait ID. And I'm going to use the one that is actually in the kernel, and you're going to see soon why I want to stick with that, and not use these ones which just translate to something else that is eventually going to go to the kernel. So let's stick with wait ID. Now you can see we have something else to include here, so I'm going to copy this. Now let's take a look at the arguments of wait ID. This is how it looks like, the signature. I'm going to go ahead and copy this. And let's read about what we need to pass to these parameters over here to make it work. I'm just going to talk about my goal with this function. Remember that this flow is happening in the parent, and the parent wants to wait for the child to finish executing the command. So what I want to do with wait is I want to wait for the child to finish. So it's going to pause the parent until the child is finished, so the parent will know when to prompt for the next command. Now we can see that it starts by talking about the ID type and ID arguments. And we can see we have here an option to wait for a specific child. But we're just going to make this as simple as possible and go ahead and wait for any child. And that's going to be p all. And remember, this goes into ID type, and then ID is ignored. So we can just pass in 0 for ID. Afterwards, we got this sig info structure. I'm not going to do anything much with it, but we need to pass it. So I'm just going to define it here, and then pass in the pointer. And finally, we got some options. And let's take a look at the options over here. We have here a couple of flags that we can specify in options. And we're just going to wait for children that have terminated. So this flag over here, W exited. Okay, now we're ready to test out the shell again. Works nicely, and we get back the prompt. Nice. But let's take a look at a problem before we can use this for our distro. First of all, you can see that the executable is 16 kilobytes, which is not bad, it's pretty small. But here's the problem. This is a dynamic executable. If I run LDD on the shell, we can see that this is not a static executable. It requires, for example, the libcso shared object. So what I'm going to do to fix this is I'm going to use the same GCC command, but pass in -static. But check out what happened. Now it's suddenly 750K. This is quite a large size for such a small program. But at least it's not a dynamic executable anymore. So this is fine, this will still work nicely, but let's go ahead and make this even smaller. Well, for this we're going to need to write a little bit of assembly. What we're going to do here is we're going to make the system calls by ourselves, not through the C library. We're going to implement these functions: write, read, execv, and finally wait ID. Let's start with write. So I'm going to open a new assembly file, and let's call this file sys.s, because this will be our connection with the system. I personally prefer the Intel syntax. I know that in the Unix world there's the AT&T syntax, which is really prevalent, but I find the Intel syntax much more clear. And we are going to use the GNU assembler. So I'm going to start with using the Intel syntax directive. And let's also open the info page for AS, which is the GNU assembler. And I'm going to open the entry about Intel syntax. By the way, I opened this search here by pressing on I. So you can see it talks about the Intel syntax here, selects Intel mode. We also have an optional argument which is called prefix, or no prefix. And I'm going to use no prefix because this will specify that we don't require the % prefix on the registers. Afterwards, I'm going to make my symbols global, so the linker will know about them. And we're going to start just with write for now. Now let's implement write. What is write going to do? We're going to want to select the system call. We don't know the number yet, but we're going to find out soon. We're going to make the system call by running the syscall instruction. And finally, I'm going to return back. Now let's see how we can find out the number of the system call. For this, we're going to go to the source code of the kernel. Afterwards, the arch directory, architectures, x86, include, generated, ASM, and then over here to the syscall64.h file. And here we got the numbers from the kernel itself. So as we can see, write is number 1. Now this closes the deal for write, but let's go ahead and also implement read. As you can see over here, read is system call number 0. Now let's do this for fork. Fork is 57. And finally for wait ID, which is 247. But hold on for a second. We're going to have a little problem here. Notice that write uses 3 arguments, read uses 3 arguments, and fork doesn't have anything. But in wait ID we have here 4 arguments. Now we got a couple of problems with the wait ID function which we need to fix. First one is that the actual function in the kernel does not have 4 parameters, but it has a 5th parameter. And we can see this in the documentation. If I open the man page for wait ID, notice this little comment over here. This is the glibc interface. See notes for information on the raw system call. So let's go ahead and see the notes about this. So I'm just going to search for wait ID across the document. The raw wait ID system call takes the 5th argument of this type. And we can see that this argument can be null. So that's what we're going to do. I want to pass in the 5th argument. And just gonna be 0. Now what I'm going to do is, because it's going to have now a different signature than from the standard library, I can't use the header files for this anymore. So I'm going to use this as a prototype. So I'm going to copy this and put it over here. Now we're just declaring that this exists. We're going to define this in the assembly, of course, but I'm going to call it real and then wait ID. And put here the fifth argument that they're talking about over here. Now, as you can see, this fifth argument is a pointer. Since I don't care about this argument, we're just going to put here void and then start. And now let's go back down here. And instead of just calling wait ID, we're going to call real wait ID. And we'll go here to the assembly. Change the name here as well. Let's make all these global. Now, one more thing about this wait ID thing. Notice that now we have 5 arguments. I want to talk about something. As you can see over here, I'm in Wikipedia in the x86 calling conventions page. And over here we can see that the System 5 ABI of AMD64. ABI, by the way, stands for Application Binary Interface. And these are the registers that are used for parameters in the System 5 ABI. These are not the exact ones as the kernel uses. The kernel uses slightly different registers. You can see that they're almost the same. RDI, RSI, RDX. But it doesn't use RCX for the 4th argument. It uses R10 instead. So we're going to need to fix that before making the system call. So we're going to take whatever is in RCX and transfer it into R10. Let's fix that. We're going to take whatever is in RCX and put it in R10. And this will fix this up. Because remember, C is calling this function as it's a regular C function in your program, but we're going to make a system call here, so it's a slightly different interface. If we want to know the reason behind this, if we take here a look at the Intel spec, this is the syscall instruction that we just used. And you can see that the syscall instruction uses RCX for saving the return address of where to come back after the system call. So this is the reason it can't use RCX. It's already used by the syscall instruction in the CPU. Nice. So we got rid of the dependency upon the libc library. Let's go ahead and try this out. So now it's gonna be a little more complicated to build this. We're gonna go through it step by step. First of all, let's delete the shell binary we just built. And notice, first of all, we have 2 files over here. First one is the C file and then the assembly. So let's start by just compiling the C file. gcc-c, compile only, shell.c. And now we have shell.o, the object file. And now we're gonna assemble the assembly. For this, I'm gonna use AS and just pass in the assembly. Notice that it calls it a.out. So this is the built assembly, and this is the built C code, but it's still not ready to run. We need to link them together. And for this, I'm gonna use the LD linker. We're gonna call the output shell. I'm gonna pass in both of the object files. So first of all, shell.o, and then a.out. I'm gonna pass in -- entry, main, because our entry point is called main. Remember, that's the entry point for our C code. And also something important, I'm gonna need to specify this parameter over here, -z, and then no exec stack. And this will tell the linker that I don't want to have an executable stack. Looks like we forgot to define the execv system call in our assembly, so let's fix that real quick. So right after here, read, I'm gonna define also execv. And let's search for execv over here. And that's number 59. Nice, so we're done with this. Let's check it out again. This time I only need to assemble this again. And then run the LD command, as before. And I forgot to make it global. Global makes it visible to the linker. Now there is one more thing I want to fix here in the code. Notice that after execv over here, in case it fails, we break. But where does it break into? Well, this for loop over here, the execution of the code goes right over here. But since our entry point is now called main, we don't have a C library anymore. So this is the actual entry point of the executable, not some entry point by the C library. We need to take care of exiting from the program. So at the end of the main function over here, we're going to call the exit system call and pass in 0, for example. Now we need to also implement this in the assembly, as we did with the other system calls. So let's open up the assembly file, sys.s, add here exit as well. And I'm going to open the file from the kernel again. And here it is, sysexit is number 60. Technically, no need for this return. Yeah, we can remove it because it's no return. Now let's go ahead and build it again as we did before. So I'm going to start by running gcc-c on shell.c. Afterwards, we're going to assemble this. And then I'm going to run the ld command that we ran before. My bad. Also the global. We need to first of all assemble this again first. And then we're going to run ld. Now it works nicely. Now let's check it out just real quick. And nice, the shell works nicely. Let's check out the size for a sec. As you can see, it's only 9.1K, very small. Now let's go ahead and pack this into a init ramfs that we can use with our distro. But first of all, I want to go ahead and change the name of this to init, because this is the default name of the init process. And now I'm going to create an archive with this file. I'm going to start by echoing the file I want to include in the archive, echo init. Then I'm going to pass this into cpio-h, new C. This is the format that the kernel supports. -o creates new archive. And I'm going to pass this into init.cpio. And now we have the archive over here. Now let's go back to the Linux source code. I'm going to run here make help again. This time let's take a look at an interesting option here that is called isoimage. This creates a boot CD-ROM image, and it makes it at this path over here. We can even specify arguments for the booted kernel with fdargs and the init ramfs right over here. So let's use this. I'm going to start by specifying the fdargs. Make isoimage. Let's start by specifying the fdargs. Here I'm going to specify the path of the init ramfs on the disk image itself, which is going to be at /init.cpio, as we call it ourselves. I'm going to do this by specifying initrd equals /init.cpio. Next, I'm going to specify fd initrd. And here we're going to specify the path on our host machine of where it can find the CPIO that we just created. And this is going to be right over here. And let's run this. Nice, and we can see the ISO image is ready. So I'm going to copy this and we're going to use QEMU again to test it out. This time I'm going to use the CD-ROM option. Nice, and it's booting up. And we can see the shell here is working nicely. But we can't do anything, right? It's going to just do nothing because we don't have anything here except the shell itself. Let's finish off by putting Lua in our distro. The reason I'm choosing Lua is that it's a very minimal programming language that is easy to build from scratch. And we're going to make a static build of Lua, and then we're going to put it inside of the distro. So let's click here on download. And I'm going to copy the path to the tar.gz over here. Copy link. Now let's go back here to fun, and let's wget that path. Nice, and now I'm going to go ahead and extract this. Now we got the Lua directory over here. And I'm going to go here to source. We can see we have here the source code of Lua. I want to specifically open the make file because I want to make it a static build. So I'm going to scroll down here a little bit and I'm going to specify custom LD flags. This will be custom flags for the linker. And I'm going to pass here -static. That's it for the make file, so I'm going to save this. And now let's just run make. Nice, and now we have a static build of Lua. We can just make sure by running LDD and then Lua. And here it is, not a dynamic executable. Let's just make sure that it works. Nice. Now let's go ahead and put this inside of the distro. So what I'm going to do is I'm going to move this Lua executable up to my fun directory. Now we got it over here. And now we want to pass both init and Lua into the CPIO. Now files looks like this. And now we're going to create a CPIO archive from these files. Same flags as before. By the way, the size of Lua Static build is 1.4 mega, which is pretty big, but remember that Lua does require heavily the C library. There are some optimizations that we can do, like using maybe a different library, but this is out of the scope of this video. So now we got the CPIO ready. Let's make another ISO image for that. Let's go back to the kernel, and let's run make ISO image again, as we did before, with the fd-args and the fd-init-rd. And now we have here the ISO image ready, so we're gonna test this out with QEMU. Nice, so we have our shell over here, but let's go ahead and see if Lua works. So let's run here Lua. And nice, we got Lua in our custom distro. Pretty cool. Now let's just go ahead and see that we can also run this with VirtualBox. So let's close QEMU over here. And I'm going to copy this ISO image to my host computer. And let's open up VirtualBox now. Let's create a new virtual machine. Now we got the ISO image, so I'm going to specify it over here. This is the path. Here we're just going to choose other Linux. I'm going to put a very low amount of memory to show you that it works with only 32 megabytes. And we're not going to add any virtual hard disk. Just going to be from memory. Now let's go ahead and start this. Nice, and we can see it works. We got the shell over here. Let's see that Lua works. Lua is working nicely. Let's do something a little more interesting here. So let's make a for loop. Nice, everything here is working nicely. By the way, before we finish off, let's just take a look at what is the size of the ISO image right now. So with Lua, this is a size, 2.7 megabyte. But let's see how big it was without Lua. So I'm going to go back here, run the same command that we did, just with init, without Lua. And now let's run make ISO image again. And this is the smallest distro, 1.3 megabytes. And by the way, if you're curious, the ISO image option here uses a bootloader that is called ISO Linux.